Hello, and welcome back to another video in MOOCOR series. This is topic 6 of the MOOCOR series. It's the last video of Module 2. Module 2 is devoted to Simplex method. In topic 4, we discussed regular Simplex method in canonical form. We introduced the canonical form as a maximization problem with all constraints in the form of less than or equal sign and all variables to be non-negative, all of them greater than or equal to 0. We discussed in topic 5 the big M method. And big M method was part of addressing non-canonical forms of the LPs, in which some of the constraints may be in the form of greater than or equal. We learned how to address that issue. In topic 6, we are introducing a different method called Twophase method to address the same issue, namely dealing with the constraints that may be in the form of greater than or equal sign. But before we introduce two-phase method, we are going to go back to topic 5 material and discuss a little bit more about the big M method and issues related to the non-canonical forms of the LP. What we have covered on non-canonical form were related to the constraints. What about the variables? If there is a variable that instead of greater than or equal 0 needs to be less than or equal 0, how do we treat that variable? If there is a variable that can be unrestricted, can be both negative and positive, how do we address that? We also looking at the objective function. We introduce the canonical form as a maximization problem. What about the minimization problems? What do we need to do to address those? So we will cover that in this topic. We will then go back to the big M method and discuss some of the issues related to the use of M as a very, very large positive number in our calculation and keeping it as a symbolic calculation in the regular calculations that we do for moving from one tableau to the next tableau and so on. From there, we will introduce the two-phase method, which does not have the drawbacks that big M has. So let's start our topic by looking at treating non-canonical form. Let's start our discussion by looking at minimization problems. Remember that we introduced canonical form as a maximization problem with all constraint in the form of less than or equal and all variables to be greater than or equal to 0. In topic 5, we discussed the cases that some of the constraints may not be in the form of less than or equal sign. They may be greater than or equal sign or equal sign. Both big M and two-phase methods will address such a situation. What about the objective function? What do we do if the objective function instead of maximization is in the form of a minimization? How do we handle minimization problems? The process is really simple. But before we actually do that, let me take a two-dimensional example and solve it graphically. You notice that the red Z line and the direction of the increase, the Z mean and Z max and the optimal points are given as those points. Let's multiply the objective function by a -1. Now you notice that the only change that occurs is that the direction of increase on the Z line reverses, and thus the max and the min will change their respective locations. So one of the very easy approaches for us is just to multiply the objective function by a negative 1 and then solve the problem as a maximization problem. When we reach the optimality, we will remember to multiply the z solution from the final tableau by negative 1 to get the original z value. Here is an example. A minimization problem, 4 variables, 2 constraints, all variables greater than or equal to 0. I have multiplied the objective function by a negative sign, and I have converted the problem into a maximization problem. If I solve this, eventually the final tableau will be given as the one that you see in here. The optimal solution for the objective function is 22, and I will remember to multiply this value by a negative sign to get the original minimization problem value. The second method is to solve the problem just as a minimization problem. The only difference is that when you select a variable to enter the basis, we have to look at the most positive value. The optimality condition in this case is when all entries in the 0 are negative, as opposed to the maximization problem. When they are all negative, then you have reached the optimal solution of the minimization problem. In this case, my selection for the entering variable were based on the most positive value. At the first tableau x2 entered, and at the second tableau x4 enters. Finally, the optimal solution of this problem, you will notice that everything in the 0 is in the form of a negative number for the minimization problem, and the z actually shows the optimal solution of negative 22 for this problem. So minimization problems are easily handled by one of the two methods that we just discussed. What about the variables? That can also be done by simple mathematical operations. Let's look. To visually see the significant impact that these changes might have, let me take this two-dimensional example in which x1 and x2 are both greater than or equal to 0. You will notice the feasible region for this problem. I'm going to keep changing these variables to less than or equal and unrestricted and see what changes will occur in the objective function. In this case, I have changed x1 from greater than or equal 0 to less than or equal 0. You notice that the feasible region totally changed. There's nothing from the previous one in here. In this case, now I have kept x1 greater than or equal to 0, but I have changed x2 to less than or equal 0. Again, you notice the significant change. Nothing from the previous original feasible region was included. Now I'm going to change both of them to less than or equal to 0. Again, a significant change altogether for the feasible region. Now let's look at some unrestricted cases. Unrestricted means they can be both positive and negative. In this case, I have kept x2 as an unrestricted. You notice that the previous feasible region in this case is included, but a larger portion is also added to the feasible region. What if I change x1 to less than or equal and keep x2 unrestricted? Another significant change. So by changing these different cases, you can clearly see and get a feeling of what big impact this can have on the feasible region. Sometimes part of the old feasible region are included, but in majority of cases they are not included at all. Total change in the feasible region. And if feasible region changes, the optimal solution of the problem will change. A problem that had a unique solution now may even not have a solution, or it may be unbounded. So it is significant for us to make sure that we are clear about these variables, whether they are restricted, unrestricted, and less than or equal. The word unrestricted sometimes is explicitly mentioned, sometimes implicitly. We just don't mention anything about the variables. That specifically means that those variables are unrestricted. This problem in which x1 unrestricted and x2 unrestricted is specifically mentioned and explicitly written is the same as the problem that there is no mention of x1 and x2. Here is a warning, and this is a common careless but serious mistake. A lot of students, when they write the standard form of a problem, they forget to put the slack variables or artificial variables as greater than or equal sign. Not having them there indicates that they are unrestricted, and those variables are all greater than or equal to 0. So these two problems are not the same. So how do we treat these cases? We are going to exchange. We are going to exchange xj prime with a minus xj for the cases that xj variable is less than or equal sign. In this example at the right, I have changed x1 with minus x1 prime. And by making that change, now I am able to declare x1 prime as a greater than or equal sign and solve the problem. What about the cases where variables are unrestricted? Simple. We are going to do another exchange. This time we are going to replace the unrestricted variable with two variables. We're subtracting two variables in the form of, let's say, x1 prime minus x1 double prime, where x1 prime and x1 double prime are both greater than or equal to 0. And then we can solve the problem. That's how we treat the non-canonical forms. Now let's look at Big M method in a little bit more detail and see some of the drawbacks that this method has and how it can be improved by using a different technique called two-phase method. Let's first take a look at one important step of the Big M method, and that was preparation of the objective function, the 0 for the Big M method. In that procedure, we went through steps trying to eliminate artificial variables from the 0, and as such we ended up with options that would allow us to write the artificial variables as legitimate basic variables. We did that outside the tableau. We can do the same procedure inside the tableau And in this case, I just wrote the problem in the tableau, and then I recognize that R1 and R2 cannot be legitimate basic variables if their entry at the 0 is not 0. So I will do the row operation inside the tableau, and it is much easier for me to keep track of these values as I'm looking at the rows and the columns at the same time. After I process this, what I will end up with, I will call it legitimate simplex tableau. And this legitimacy is only referring to the basic variables being associated with an identity matrix or having the right format. Instead of doing it row by row, I can actually combine the rows together. If in this case I have R1 and R2, the only thing that I have to do is just add the coefficients for each column and then multiply it by -m and add it to the 0 value. Just like any other procedure, Big M has its own strengths and weaknesses. Some of the drawbacks of this method deals with the magnitude of M that can be set to reasonably high value considering the coefficient of the decision variable in the problem. For one problem, 100 may be large enough. For another problem, 1 million may not be. And these very large values assigned to M might make comparison difficult for close values considering the error on the decimals. The other one deals with the symbolic calculations, and unless M is assigned a value, calculations involving M must use the symbol M throughout the calculation. Only some special math software do symbolic calculation, and even after feasible extreme point is reached, the complete tableaus are processed including the artificial variable columns. Now remember that in Big M, reaching the optimal solution is our goal, and in this process we theoretically may be possible to just go through as many adjacent infeasible extreme points until we get to the optimal solution. What if we change our goal from reaching the optimal solution of the problem to reaching a feasible solution first? And that is the essence of the two-phase technique. In our discussion of the two-phase, we will be seeing how phase 1 problem is set up, how phase 2 problem is set up, cases of problems with no feasible solution, and advantages of the two-phase over Big M. In phase 1, we are going to set up the standard form of the constraints, add artificial variables, create phase 1 objective function, which is a minimization of the sum of all artificial variables used, and then we will set up the initial tableau and we will legitimize that, and then we will find the optimal tableau for phase 1. If any artificial variable remains in the optimal solution and it is greater than 0, then we will stop because problem is infeasible. Otherwise, we will use phase 1 tableau and we will go to phase 2. Let's show the steps of the procedure with an example. It's the same example that I used for the Big M method. It's a 4 variable problem maximization. 2 of the constraints, one of them is greater than or equal and one of them is equal. So following the steps, we would write the standard form of the constraints. We will add artificial variables to this set of standard form of the constraints, and now we have 2 artificial variables. So we will write the phase 1 objective function, which is minimization of sum of all artificial variables used, in this case 2 artificial variables. So we will start setting up the tableau. We will write the tableau based on the information that we have. Tableau is not legitimized, so we will go through the legitimization of the tableau by using the row operation, and we will identify the legitimized tableau for phase 1 of the problem. From here, we will continue the regular procedure for the simplex method. Notice that this is a minimization problem, so we will select the most positive entry at the z prime row. Well, we'll go through the steps identifying, entering and leaving variables, and at the end of phase 1 we will come up with the optimal solution of this phase. Note that in this final optimal tableau of phase 1, none of the artificial variables are present in the basis. Both of them are non-basic and equal to 0. So this solution actually represents a feasible extreme point for the problem. From here we will end phase 1 and we will start phase 2. The first thing that we do in phase 2 is to drop the non-basic artificial variable columns from the optimal tableau of phase 1. In case that there is an artificial variable in the basis with the value of 0, there is a discussion about that at the end of this video. However, we are assuming that that's not the case, and we will replace the z prime row with the 0 of the original maximization problem in a standard form. Then we will legitimize the tableau and we will solve it using the regular simplex iterations. In here I have taken the optimal tableau of phase 1. I have replaced the z prime row with the 0 of the original problem. However, just looking at this, I will realize that x2 and x3 as basic variables need to have 0 entry at the 0, and they do not. Therefore, I will perform row operations to make them 0. After I legitimize the tableau, I will realize that this is a maximization problem and I have negative entries at the 0, so I will go ahead, just a regular method, find the most negative value in the 0, calculate the min ratio and iterate. In the next tableau I realize that I'm still not optimal, so I will pick up the most negative value in the 0, and there is only 1. I will calculate the mean ratio and entering a leaving variable, and I will come up with the optimal solution. This is the same optimal solution that I have found in the big M. So let's now compare these two tableau sets that I have with each other, the Twophase and the big M. Notice how similar they look. First of all, the entries inside the tableau are the same, and the only difference is in the values of the objective function row. But if you look clearly, you will see the similarities, and those similarities are exactly what we are interested in. In this case, as we go to the phase 2, we will have exactly the same values for the objective function rows. In phase 1, however, the coefficients of M in big M method tableaus are the same as the entries at the z prime row, except with a difference in the sign, because one is a maximization problem and the other one is the minimization problem. So as we saw, two-phase method is a more efficient and easier procedure than big M. Less hassle, symbolic calculations with M, and at the same time, because it does not keep artificial variables in phase 2, problems become smaller and easier to solve. There is one additional important point to make about the two-phase. At the end of phase 1, we are dropping the artificial variables that are not in the basis. Obviously, if at the end of phase 1 artificial variable is in the basis with a positive value, that problem is infeasible. What if artificial variable is in the basis but it has a value of 0? At that point, we do have a feasible solution. We are at a feasible extreme point, so we can start phase 2. But we cannot drop that artificial variable from the tableau because it is in the basis, and if we drop it, then we don't have anything to replace it, and we will lose one of our basic variables. Let's see how these cases are handled. I have taken an example of 4-variable 2-constraint problem. I have written the phase 1 problem, and I have gone through the proper steps to identify the necessary tableaux for this problem, and I have ended up with an optimal solution for phase 1. But I realized that I have R1, an artificial variable, in the basis with the value of 0. So this is actually a feasible solution that I have at the end of phase 1. So I will start setting my phase 2 problem. I would rewrite the original objective function in a standard form in the tableau of phase 1, and then I would legitimize the tableau. Now this is a maximization problem, and x1 entry in the 0 is most negative, so I will enter x1. R1 is not a candidate because that has a negative value on that column. Here x3 is the only candidate, so I will carry the iteration, and as I carry the iteration I will notice something very strange happening, that R1 now becoming a positive value, which indicates that I started from a feasible extreme point and I ended up at an infeasible extreme point. How can this be fixed? Let's take a closer look at the tableau and see what we can get from that tableau. This is the legitimate tableau of phase 2 problem. We can rewrite the equations associated with this tableau for the 0, for the x3 row, and for R1 row. These are 3 equations. I can write them. And since R1 is 0, I can eliminate R1 in the last equation but by eliminating R1 I will lose one basic variable from my tableau. To find the basic variable for my tableau, I should just pick another one of the non-basic variables from the set that I have. Looking at the equations, I notice that S2 is a very good candidate. Its entry is negative at the R1 row, but because the right hand side is 0, I can actually multiply the whole row by a negative sign, and I would end up with a legitimate basic variable for my tableau. Place it in there, carry the iteration, and you will have the optimal value of the problem. Note that I didn't have to actually use S2. I could have selected X1 or X2 or even X4 as the basic variable, but S2 was an easy choice, so I selected that one. With this lecture we have finished module 2. We will start module 3, which relies heavily on the background and your knowledge in linear algebra. If you have not had a linear algebra course, or if you are not familiar with the vectors and matrices, I would suggest that you check khanacademy.org material and videos and take a look at the lectures on that site. Excellent lectures, and they would cover everything that we need and beyond that. I will cover some of these material, but it is an excellent idea if you have the proper background, so within the 30 minutes or so videos that we will have for this MOOCOR, we can cover as much as we can. As I'm leaving you, I will let you go through one example by yourself.